Probabilistic fallacies are formal fallacies because they involve reasoning which violates the formal rules of probability theory. Having a basic knowledge of probabilities will surely help you spot such fallacies. However, common sense can be enough to identify some of the most obvious ones. In this video, we'll evoke two examples. The first one is the Hotend Fallacy, and we will not dwell long on it because it's easy to grasp. It corresponds to a failure to understand statistical independence. That is, that two events are statistically independent. Let's take the traditional example of the roulette at the casino. Let's say that there was a streak of reds, 4 or 5 reds in a row, and now that you have to bet $100, are you going to bet on red or on black? Well, if you say red because you are on a winning streak of reds, then you do not understand how probabilities work and that such patterns are bound to appear randomly. Unless someone has been cheating, and it usually does not go unnoticed, there's exactly 50% chance that it will turn out red and 50% that it will turn out black. The events are independent from one another regardless of what happened before. And if you claim otherwise, then you are committing the Hotend Fallacy, and it's a form of superstition. It's a famous fallacy, but it's not my favorite one because anyone with common sense will know that. I personally, when it comes to probabilistic fallacies, have a preference from one that is called the confusion of the inverse. To understand this one, I need to introduce you to the concept of conditional probability. You'll see it's very easy, and the coronavirus is, as usual, perfect to provide examples. So first, how to write conditional probabilities. If you already know about the concept, you can skip this part, by the way. So this symbol means probability of event A knowing that event B is true. It's very simple. Let's say that you got the coronavirus and you read that 3% of people who contract the disease die. In other words, the probability of death equals 0.03, which is another way of writing down 3%. Remember that probabilities are always comprised between 0 and 1, by the way. 0 means it's impossible to happen, and 1, it's 100% sure that it is going to happen. So now that you are not sure about the numbers, so you call a random doctor, someone recommended to you, and you ask him anxiously, do I have a 3% of chance to die from the coronavirus? Well, as he should, he asks you, how old are you? Because if you are young and healthy, let's say below 50, the probability to die is extremely low, like 0.1% maybe. But if you are above 70, then maybe it's above 5–10%, depending on if you have comorbidities. So let's write down this in terms of conditional probabilities. Probability of death, knowing that you are young and healthy, equals 0.001. Probability of death, knowing that you are above 70, 0.15. I don't know if those numbers are correct right now, but you get the general idea. With those data, now the doctor can answer you with more precision. Okay, now that hopefully you understand the symbols that I'm using, the underlying concept, let's talk about the confusion of the inverse, also called the conditional probability fallacy. You are committing the fallacy if you believe that the probability of B knowing A is roughly equivalent to the probability of A knowing B. I'll give you the traditional example of drug consumption. Let's assume two things. First, that half of the people that consume coke also consume marijuana, cannabis. We can write it that way. The probability that you consume marijuana knowing that you consume coke is 0.5. Now, you just discovered that one of your friends consumes marijuana, cannabis, and I'm asking you what is the probability that he or she also consumes coke? Well, if you reply, based on prior knowledge, 50%, then you are committing a fallacy. It is probably way lower because the vast majority of people who consume cannabis do not consume coke. And you cannot infer the probability of A knowing B because you know the probability of B knowing A. you would need additional data to answer my question. The fact that you know that half of the people who consume coke also consume cannabis, marijuana, does not give you any information whatsoever on the proportion of people who consume coke among the people who consume marijuana. There are a few other examples of probabilistic fallacies, and if you are eager to know more about them, look for conjunction fallacy or the Basel rate fallacy, but I have got to warn you, these ones are a bit trickier to understand.